And you'd expect that something as physical as volume would be very, very easy to compute. Nonetheless, I'm going to write down the determinant right now, and here's how you do it. You take one from each row and one from each column, and I'm going to do it like this. So let's pick A from the first row, and E from the second row, and I from the third row, A, E, I, and all of that slants to the right. And then here I'll put in an A, F, H. Now I'm just going to start writing down things. Then B, F, G, minus B, D, I. And now I'm going to do C, D, H, minus C, E, G. And if you work it out, you'll find that these are the 6 ways that here I can pick one element from row 1, and one element from row 2, and one element from row 3. And I've arranged things so that every one of these picks exactly one element from each row and exactly one element from each column. So it's a little clearer if I do it like this. A, E, I, I'll start here and connect it like that. A, F, H, I'm going to go off in this direction and go back like this. And then B, F, G, I'm going to go here, here, and then wrap around. And then B, D, I, here, here, and then wrap around. So basically, from each of these guys on top, I'm going to draw 2 lines, and if it slants to the right, I'm going to put it in with a plus sign, and if it slants to the left, I'm going to put it in with a minus sign. So the determinant, if you work it out, these are the parts of the books that I always skipped. The determinant doesn't just have a geometric interpretation, it has an algebraic interpretation. It's a polynomial in the matrix coefficients, and you can show if I interchange any 2 rows, the determinant changes signs, and if I interchange any 2 columns, the determinant changes signs. And we say, gee, this determinant doesn't just have an elegant algebraic interpretation, it has an elegant geometric interpretation. We've actually tiptoed up to algebraic geometry here. You can understand the determinant either in terms of antisymmetric polynomials, or you can understand it in terms of the determinant, or you can understand it neither way, but just say both MATLAB and Mathematica have really fast routines that if you give it a symbolic or a numerical matrix, it will calculate the determinant really, really fast. In particular, if this is an n by n matrix, the determinant will return after order n cubed operations. And that's because basically what they do is they find a coordinate system where this matrix is diagonal, and the determinant of a diagonal matrix, all you have to do is multiply the rows on the diagonal. So it achieves its speed basically by exploiting this geometric insight. If you find the right coordinate system, this matrix is great. Come on in, we'll finish in 90 seconds or so. And we'll have some food left over for you guys.
Oh, okay. As usual.
Just invite them in here. Okay, so now to finish here, gee, that's kind of complicated. How complicated is the permanent? The permanent is easy. Just ignore the minus signs. Make them all plus signs. But in terms of algorithmic efficiency, the 2 things change. First of all, the geometric interpretation is lost. Instead, there's a combinatoric interpretation. And the second thing is your code slows way, way down. There's no known efficient way to calculate the permanent other than to just add up all of these polynomials. And every time you add a new polynomial, you get enormously more polynomials to add. So that's why neither MATLAB nor Mathematica include a permanent subroutine. You can write one, and you might as well write one, because there's no efficient way to do it. And there are very good reasons to think that even in principle there is no good way to do it. Yeah, you guys finish up. We're done.